Welcome to the deep dive. Today we're jumping straight into composite materials. You've likely encountered them.
Oh, definitely. They're everywhere now.
Exactly. These lightweight, super strong materials are showing up all over the place. But what makes them so special compared to, your standard metals or plastics?
Well, a lot, actually. We've looked at a ton of research, and the advantages really stand out. Things like being incredibly light, surprisingly flexible sometimes, and super resistant to rust and wear. Plus, they have impressive ability to handle impacts and repeated stress, fatigue strength.
Which explains why they're increasingly the go-to replacements in aerospace, cars, all sorts of industries.
That's right. The core idea behind composites is, well, cleverly combining different materials. You have a main body, the matrix, and then something that reinforces it.
Kind of like steel bars in concrete.
Exactly like that. A perfect analogy. They're carefully chosen to create specific engineering properties that neither material could really achieve on its own.
Yeah.
Fiber-reinforced polymer composites, or FRPs, are a great example. They're really attractive for their high specific stiffness and high specific strength. That's basically how rigid and strong they are for their weight.
Crucial for making things light but tough.
Precisely. And you can combine that with controlled anisotropy.
Anisotropy, what's that exactly?
Good question. It just means the material's properties are different depending on the direction you measure them. Think of wood grain strong along the grain, easier to split across it.
Got it.
FRPs let us control that directionality, making them incredibly versatile, and the range of products is huge. Pressure vessels, industrial scrubbers, hoppers, hoods, ducts, fans, stacks, pipes, pumps, even pump bases, valve bodies, elevator buckets, heat exchangers, you name it.
Okay, so that's combining materials. But our sources also mentioned something called functionally graded materials, FGMs. That sounds different.
Right,
like the material itself changes.
Exactly, you've got it. With FGMs, the mix of materials isn't uniform. The composition, the recipe, it changes gradually, or maybe in steps across the material.
Okay, why would you do that?
Well, what's really interesting is that this allows us to design materials that can do multiple jobs at once, even things that seem, contradictory in a normal material.
Like what?
Imagine needing something super hard on the outside for wear resistance, but flexible on the inside to absorb shocks. FGMs can potentially do that. Chapter 4 in One Source really dives into their definition and manufacturing.
Right. So the goal for us today in this deep dive is to really get a handle on these composite materials.
Yeah, explore the different kinds, how they're put together.
What makes them tick, their properties, and just see the wide range of applications. We want to give you a clear understanding, the key info, without getting totally bogged down.
Sounds good. Let's start with the basics then, the building blocks. The matrix is like the foundation.
Okay.
And in advanced composites, thermoset resins really dominate, much more than thermoplastic.
Thermosets, those are the ones that cure permanently, right?
Exactly. And the process is fascinating. You typically add a curing agent, the hardener, to the liquid resin. Then you soak the reinforcing fibers in that mixture, and finally apply heat or pressure to cure it solid.
And epoxy resin kept popping up in our research. What's the deal with epoxy? Why is it so common?
Several key things. Epoxies generally have quite small molecules, and importantly, they don't shrink much when they cure, maybe 1 to 5%.
Which is good for keeping the final shape accurate.
Critical, yeah. You can also partially cure them and store them, which adds flexibility for manufacturing. And once they're fully cured, they have excellent strength, hold up well to heat, and they're very resistant to chemicals and corrosion.
What about temperature limits?
Their glass transition temperature, that's when they start to soften, can range from a decent 100 degrees C up to a pretty high 270 degrees C.
But they're more expensive, right?
That's the trade-off, yeah. More expensive than, say, polyester resin. And it's worth remembering there are many types of epoxies, from thin liquids to solids, and that curing agents, things like aromatic amines, MDA, DDS, is absolutely crucial for the final properties.
Okay, so the matrix holds it all together, but the reinforcement, that's where the strength comes from mostly.
Yeah.
Our sources mention aramid fibers like Kevlar. Everyone knows Kevlar.
Exactly. Kevlar is a type of aramid fiber made from aromatic polyamides. They have a really unique property set. Incredibly high tensile strength and stiffness. That's the bulletproof vest magic. But also good temperature stability. They don't change size much. Good flex performance. You can process them like textiles, and they resist chemicals well.
We saw a table comparing them.
Right, table 1.3. It compares aramids like Kevlar 49 to E-glass, S-glass, high-strength carbon fiber. You see differences in density, strength, stiffness, how much they stretch.
And Kevlar seemed pretty light, but still strong.
Yeah, it's lighter than glass or carbon, but offers amazing strength and a good balance of stiffness and flexibility.
Okay, so we've got our ingredients, maybe an epoxy matrix, Kevlar fibers. How do we actually make things? Pultrusion was one process mentioned. Sounds like pulling plastic through a hole.
Huh, that's a pretty good way to think about it. Pultrusion is a continuous process, great for making parts with a constant shape, like a beam or a rod.
As it were.
You pull fibers from spools, run them through a resin bath so they get totally soaked, then through some guides to shape them, and finally into a heated die, a mold. That's where the thermoset resin cures and hardens into shape.
And it just keeps coming out.
Yep, continuously pulled by rollers and then cut to length. The trick is getting the pull speed and the die temperatures just right for uniform curing.
Makes sense.
Our sources mention mathematical models, like from Trevisano's group, to optimize this. And other factors matter too: how packed the fibers are, mold release agents, the hardener type. They all affect the surface quality, as Isfonda found.
And people are tweaking this process.
Oh yeah. Making composites with foam cores, using microwaves to speed up curing. That's MAP, microwave-assisted pultrusion. Meth's been looked into that.
So pultrusion, great for high-volume, simple, consistent shapes, but not for complex stuff.
Exactly. It's efficient but limited in geometry.
Right. So for more intricate parts, curves, varying thickness, resin transfer molding, RTM, that sounds more involved.
It is, but it gives you much more design freedom. RTM uses a closed mold.
What do you mean?
The final part has a smooth, molded surface on both sides. Really high-quality finish, ideal for complex shapes.
How does that work?
You place a dry fiber preform like a fabric shape inside the mold, clamp it shut, and then inject liquid resin under pressure. It flows through and wets out all the fibers.
Then you cure it and open the mold.
Precisely. But it has downsides. The molds are heavy, expensive, they need to withstand that pressure. There are size limits, and if the resin misses a spot, you get unimpregnated areas, which means costly scrap.
But it's improving.
Definitely. Things like high-speed RTM, using through-thickness flow channels like Han worked on, using computer simulations, CFD, to optimize mold filling.
Predicting problems before they happen.
Right. Mathematical models for void formation, like Yang's work. Even optimizing for manufacturability itself. So RTM, complex, high-quality parts possible, but higher costs and potential waste.
Now, one source mentioned a newer technique, rubber pressure molding, RPM.
Yeah.
Using rubber. How does that work?
Yeah, this one's pretty clever. One source showed a cooler pump cap made this way. The setup uses a split steel die for the outer shape, a steel cone, and crucially, a flexible rubber punch.
Right.
You put your resin-wetted fiber preform between the steel die and the rubber punch. Then a hydraulic press pushes the steel cone, which presses the rubber punch.
Forcing the preform into the mold shape.
Exactly. The rubber helps distribute the pressure evenly. Then you cure it maybe 16 hours at room temp, under about 0.65 MPa pressure in the example.
And the rubber itself matters.
Immensely. Table 3.2 showed different rubber formulations. The hardness, controlled by adding carbon black filler, affects how pressure is distributed and the final composite properties.
Like what properties?
Things like interlaminar shear strength, ILSS, how well layers stick together, and something they called crushed strength. Figures show these change with rubber hardness.
Is there an optimal hardness?
Seems so. Around 30-60 parts carbon black per 100 rubber, giving a shore a hardness of 70-80, looked like a sweet spot for overall performance.
Interesting. So the flexible rubber element is key in RPM for good pressure and bonding.
That's the takeaway. It's a neat approach.
Okay, so we know how they're made. What about performance?
Yeah.
Impact testing seems critical, especially if parts might get hit.
Absolutely. In-top tests tell us about toughness, the ability to absorb energy without fracturing. A common one is the falling weight test.
Dropping something on it.
Pretty much. You drop a weight onto a sample, it lets you analyze energy absorption, damage types, how shock waves travel, stress concentrations, all sorts of things.
Any other impact tests?
The notched IZOD test is mentioned, especially for composites with specific fiber end shapes. Results depend on the matrix, the fiber ends, fiber length.
That sounds complex.
It is. The sources break down toughness into components like energy for deformation, for pulling fibers out, for creating new crack surfaces. Equations 2.20 to 2.22 cover this.
Fiber pullout sounds important.
It often is, especially in thermosets with carbon fibers. Equations 2.23, 2.24 get into that, introducing the idea of a critical transfer length.
Which is?
The minimum fiber length needed to effectively transfer load to the matrix before the fiber just pulls out. So yeah, impact performance is intricate, depends on micro-level stuff like fiber matrix bonding.
And under normal loads. Elastic properties. How do engineers predict stiffness?
Well, simple models like the rule of mixtures help. Equation 2.36 predicts stiffness along the fibers. And for many polymer composites, the fibers are way stiffer than the matrix.
So the fiber properties dominate.
Pretty much. E1, the longitudinal modulus, is roughly the fiber modulus times the fiber volume fraction. For stiffness across the fibers, the Jones model is simpler, assumes equal stress, ignored some effects.
What about short fibers, randomly oriented?
Right. If the fibers are short but still longer than that critical length, their orientation is key. Equations 2.44 to 2.46 give estimates for random orientations, using factors to account for whether it's random in a plane or in 3D.
So prediction relies heavily on fiber amount and orientation.
Especially when fibers are much stiffer than the matrix, yes.
Okay, but real-world conditions aren't always gentle. Heat, moisture. How do composites handle those?
That's a really crucial question. Polymer matrix composites especially can be sensitive. Hashemi's study on carbon fiber peak composites looked at temperature effects on interlaminar fracture toughness, ILFT.
How well layers resist peeling apart?
Exactly. Between 20 and 130 degrees C, they found ILFT actually increased with temperature, which is maybe counterintuitive.
Interesting. Anything else?
Well, there's work on electrically conductive polymers, ECPs. Using insulating polymers as the matrix can improve physical properties, but sometimes there's a trade-off. Better mechanicals might mean lower conductivity. Equation 2.55 touches on that.
So environmental factors matter a lot in design.
Hugely. You absolutely have to account for them.
Fascinating. We also saw mentions of more advanced functions, piezoelectric composites for actuation, materials that can move.
That's the idea. Piezoelectric materials generate charge under stress and deform under an electric field. Very useful for actuators.
But their properties change.
They can be frequency dependent, yeah. Research focuses on testing methods for piezoelectric fiber composites as structural actuators. Using special interdigitated electrodes helps align the electric field with the fibers for better performance.
Applications.
Things like actively controlling the twist of helicopter rotor blades. It shows composites can be more than just strong and light, they can be active.
And joining composite parts together. That must be critical for large structures.
Absolutely critical. Joint strength is key. Just knowing the laminate strength isn't enough for predicting joint performance.
How do you improve joint strength?
One way mentioned is reinforcing with titanium. That showed big strength increases at joints 80% on axis, a huge 180% off axis compared to plain carbon fiber.
Wow.
And with enough titanium, maybe 54%, you can get bearing strength similar to a titanium alloy. Also, how tightly you torque the fasteners matters for bearing strength.
So joints need careful design, maybe hybrid materials.
Definitely. It's a whole area of study.
We also saw the term rheology. It sounds like fluid flow.
It is the study of flow and deformation. And yes, while often linked to liquids, it applies to complex materials like composites too, especially long fiber thermoplastics or even nanocomposites with carbon nanotubes.
Why?
It affects how they process, how they flow into molds. Cervenka and Allen looked at long fiber thermoplastic rheology. And figure 2.21 showed how stiffness and viscosity of nanotube composites can depend on frequency.
Anything else on rheology?
Just a crucial reminder, with any new materials, especially nanoparticles, biological characterization and toxicity studies are really important.
Good point. Okay, we've covered fundamentals, manufacturing, behavior. Let's shift to some advanced types and applications. Functionally graded materials, FGMs. Let's dive deeper there.
Right. FGMs open up so many possibilities. The general process involves preparing powders, creating that compositional gradient-controlled blending or segregation, then consolidating it, usually with heat and pressure.
What kinds of combinations?
Metal, ceramic, ceramic.
Yeah.
You can even grade the pore size throughout the material.
And the main uses for this gradient?
A huge one is thermal barrier coatings. Think jet engine afterburners, combustion chambers, places with extreme heat.
How do FGMs help there?
By gradually transitioning from metal on the cool side to ceramic on the hot side, you minimize the thermal expansion mismatch. Less stress, fewer cracks, longer life.
Makes sense. Other areas?
They're being explored for thermoelectrics, photoelectrics, nuclear energy. though often not full-volume FGMs there because of cost. The key is designing components to handle multiple conditions or functions by controlling composition locally.
How do you actually check these complex FGM structures? Verify the gradient.
A whole suite of techniques. Density, porosity measurements, optical microscopy to see phase distribution, X-ray diffraction to identify the crystal structures present.
What about performance testing?
Things like creep testing, how they deform under load over time, and measuring how properties like the coefficient of thermal expansion, CTE, vary across the thickness, which causes thermal stress.
We saw examples in polymers, too.
Yeah, graded cross-link density in rubber, changing stiffness in polyurethane nanocomposites, shifts in the glass transition temperature in rubber, and a big one, biological prostheses.
Why FGMs for implants?
Better matching the properties of natural bone and tissue, minimizing material mismatch. You can even grade porosity to encourage bone ingrowth, like with those nanohydroxyapatite PVA biocomposites.
So characterizing FGMs means looking at structure and property variation.
Exactly. You need the full picture.
Okay, going even smaller. Nano and micro composites by electrodeposition sounds very precise.
It is. It's like building materials atom by atom, giving nanometer control. It happens under non-equilibrium conditions. You can create unusual structures, amorphous, nanocrystalline, metastable phases, things you wouldn't normally get. And it's done at low temperatures, low energy, relatively low cost compared to vacuum methods.
How do particles get included?
Figure 5.4 showed a mechanism involving ionic clouds, movement in the liquid, diffusion. It's complex electrochemistry at the surface.
And applications for this?
Catalysis, energy, like platinum ceria composites for alcohol oxidation, magnetic nanocomposites too, gold, cobalt nanowires, copper nickel nanolaminates. They have unique nanoscale strengthening mechanisms.
Other benefits?
Gradient nanolayered composites show better wear resistance. Systems like zinc cobalt nanolayers have improved corrosion resistance. So electrodeposition lets us engineer materials atom by atom for unique properties and cost-effective high-tech uses.
Moving on slightly. Short carbon fiber reinforced polycarbonate. Why short fibers? What's key there?
Getting those short fibers evenly dispersed in the plastic is crucial. You can do it by mixing dry powders, using solutions, or melt mixing, which is common.
And the effect of adding fibers.
The source looked at polycarbonate with 15% carbon fibers made by melt mixing and injection molding. Adding fibers increases tensile and flexural strength, and modulus makes it stronger and stiffer.
But
it reduces elongation, makes it more brittle. And impact strength can actually decrease if the fiber matrix bond is weak or there just aren't enough fibers.
How about other properties?
Dynamic mechanical analysis shows increased stiffness over temperature, maybe a slight shift in the softening point. Interestingly, higher fiber content could slightly lower the degradation temperature, maybe more active sites at fiber ends.
So it's a balancing act with short fibers.
Definitely. Balancing strength, stiffness, brittleness, impact resistance, thermal stability, requires careful control of fiber content and bonding.
We also saw ionic polymer metal composites, IPMCs, artificial muscles. That sounds like science fiction.
They are really intriguing electroactive polymers. They convert electrical energy to mechanical motion and vice versa, hence artificial muscle.
What are they made of?
Typically a thin ionic polymer membrane sandwiched between metal electrodes. Apply voltage, it bends. Bend it, it generates voltage.
Several uses.
Actuators, sensors, MEMS, fuel cells, biomedical stuff. They're light, flexible, but currently quite expensive, which limits things.
How do they work?
Equations showed it involves ion movement within the membrane under an electric field. This causes swelling or shrinking on one side, leading to bending. Voltage, ion type, lithium versus sodium thickness all affect how much they move.
So lightweight, flexible devices that respond to electricity. Cool.
Very cool potential, yes.
And, of course, we have to talk about nanocomposites with carbon nanomaterials, nanotubes, graphene. Huge buzz around these.
And for good reason. Carbon makes incredible structures at the nanoscale. Studies on multi-walled carbon nanotube epoxy composites show even small amounts boost stiffness, strength, conductivity.
Pressure resistance, too.
Some studies report that, yes, graphene nanoplatelets, single carbon sheets, and fullerene composites are also hot areas. They can improve mechanical properties, thermal stability, like making polyethylene resist heat better.
So tiny carbon additions have big effects.
Dramatically enhanced properties, potentially.
Syntactic foams were another type, filled with tiny hollow spheres.
That's exactly it. Hollow microspheres embedded in a matrix, usually epoxy. Density is controlled by the spheres.
What are they used for?
Lots of things. Lightweight structures, buoyancy aids, thermoacoustic insulation, energy absorption like in bumpers, even manipulating electromagnetic waves.
Temperature range.
Yeah.
Other properties.
Depending on the epoxy, maybe 80 to 100 degrees C. Their dielectric properties can be tuned, making them transparent to microwaves, for instance. Adding short carbon fibers can boost their flexural strength and stiffness, too.
So lightweight, customizable properties by picking the right spheres and matrix.
That's the key advantage, yeah.
Now for the really tough stuff. Advanced carbon composites, CCs. Sounds high performance.
Extremely high performance. Carbon fibers in a carbon matrix. Because carbon, especially graphite, is so stable at high temperatures, these composites excel where others fail.
How are they made?
Processes called carbonization and graphitization. The temperature is key for final properties. Different starting materials for the fibers also matter, pan-based versus pitch-based.
And fiber arrangement.
Big impact, random unidirectional, and fabrication methods vary. Thermal degradation of polymers or pitch, or chemical vapor infiltration, CVI.
CVI.
Passing carbon-containing gas through a porous fiber preform, depositing carbon. There are variations like thermal gradient CVI, liquid infiltration, each with challenges. Sometimes polymer composites are precursors.
Where are these used?
Critical applications: space shuttle thermal protection, nuclear reactors, high-temp industrial tooling. Hot pressing is being looked at for faster manufacturing. Fiber orientation and process details are vital for strength.
So exceptional high-temp performance, complex manufacturing.
That sums it up well. Indispensable for extreme environments.
Moving to metals. Metal matrix composites, MMCs, combining metal toughness with other strengths.
That's the idea. A metal matrix, aluminum, magnesium, titanium, copper alloys reinforced with something else.
Like what?
Ceramics like alumina or silicon carbide, carbon or glass fibers, even other metals, can be continuous fibers or discontinuous particle short fibers.
Does the reinforcement type matter?
Yes. Continuous gives directional properties. Discontinuous tends to be more isotropic, uniform in all directions. Stress distribution is complex, especially with short fibers. Simplified models help predict strength.
What's most important for performance?
The interfacial bond, how well the reinforcement sticks to the metal. Crucial for load transfer, affecting mechanical and thermal properties.
How are they made?
Various routes. Liquid state like stir casting or squeeze casting. Solid state like powder metallurgy. Vapor deposition techniques too.
Other properties.
Toughness depends on many factors. Hard reinforcements boost wear resistance significantly. Managing the thermal expansion mismatch between metal and reinforcement is a key challenge.
Where do we see MMCs?
Aerospace, automotive, electronic packaging, engines, satellites, combining metal benefits with reinforcement boosts.
We also saw functionally graded polymer composites with magnetic particles, combining gradients and magnetism.
Right. A study looked at rubber with an iron particle gradient. Measuring magnetic properties, saturation magnetization, coercivity remnants tells you about particle dispersion and interaction with the rubber.
What do they find?
Magnetization varied with iron loading and position, as expected. Comparing graded samples to uniform ones showed the effect of the gradient. It's using magnetism as a tool to characterize these advanced polymer composites.
Interesting approach. Finally, ceramic matrix composites, CMCs, for extreme environments again.
Definitely. Ceramic fibers in a ceramic matrix, excellent high-temperature strength and stiffness.
How are they made? Liquid silicon infiltration.
LSI is a key method for silicon carbide matrix CMCs. Molten silicon infiltrates a porous carbon preform and reacts to form SIA. Other methods exist too, CVI, polymer pyrolysis.
Advantages.
Reaction processing like LSI allows near-net shaped parts with low shrinkage, critical for complex components.
Applications.
High-wear parts like bearings and seals, but also advanced aerospace turbine engine components, thermal protection systems, where metals simply can't survive.
And just touching on a few others quickly, ZrO2 nanocomposites, periodic glasses, even bamboo fibers. The field is huge.
It really is. Zirconia nanocomposites show how nanoscale control of structure and additives can tailor ceramic properties, magnetic, electrical, optical. Periodic glasses are pushing boundaries for solid-state batteries. And using natural fibers like bamboo shows a move towards sustainable, high-performance composites, too.
Finally, surface wettability. Seems basic, but important.
Fundamental. How liquids interact with surfaces, the contact angle relates to surface energy. Roughness and surface chemistry change wetting, explained by models like Wenzel and Cassie Baxter.
Why control wettability?
Huge range of applications rely on it. Creating specific surface textures via lithography, layer-by-layer assembly, etc., leads to superhydrophobic surfaces for self-cleaning, anti-icing, anti-corrosion, even antibacterial effects.
Wow, we have covered an enormous amount of ground today, from the basic ingredients right through to state-of-the-art applications. Composites are clearly reshaping industries.
They really are. That ability to precisely tailor properties by combining materials, plus the advances in FGMs and nanocomposites, it's allowing us to create materials with capabilities we couldn't have imagined before, even achieving seemingly contradictory properties.
So, as you reflect on all this, think about the continuous innovation, especially in manufacturing, bio-inspired designs, nanoscale control. How might these advancements transform everyday products and enable totally new technologies? And maybe, what are the biggest hurdles still remaining for even wider adoption of these advanced materials?
Good questions to ponder.
That's your food for thought as we wrap up this deep dive. Thanks for tuning in.